Okay, recording is on. Welcome everyone to the next edition of our course on generalized geometry. So today we will finally get to Courant algebroids, so the juicy stuff. But of course we will do it slowly. There was something I wanted to mention before we begin, but I forgot what it was, so let's start. So let's do introduction. So I don't need to recall now what we did last time, because last time it was a different section. It was introduction. So now we will be mildly using the facts from there. So, but let me still call this introduction, but as a subsection. So I want to kind of motivate these objects in some way. And as first part, let's do linear algebra. So forget about geometry for now. But this is kind of the important prerequisite. Okay, so disclaimer, everything from now on, unless otherwise stated, is finite dimensional and over real numbers. Over real. So, here it doesn't really matter, but then I want to do smooth geometry and so very concrete setup. So now let's make a definition which will, in a sense, mimic what we've said about symplectic stuff. So let V be a vector space. With inner product, and with A, not necessarily positive definite. Inner product. I still want it to be non-degenerate, but it can have arbitrary signature. And from now on, I will always assume, whenever I say inner product, this is what I mean. From now on, this is what it means to be inner product. Because normally people, I suppose, they would say that this is positive definite.
But it's still not degenerate?
Yes. I only realized that, it's still not degenerate. And I will put it like this. Okay. Now the definition says that a subspace of this, so we will be interested in studying subspaces of this, so let me call it linear subspace, linear vector subspace. Linear subspace U in V is called. Now we will have a similar forking as before. So we say it's isotropic if it's contained in its complement. Okay, so everything that's in U is here, which means it's orthogonal to itself. So this is the same. As to say that the inner product restricted to U is 0. Okay, just a remark. And note that just as before, okay, I will get there later. Coisotropic, if the inclusion goes the other way, is contained within, and Lagrangian if we have the borderline case. I will define Lagrangian to be the same but with equality. So it's the one which is both isotropic and coisotropic. And just as we had before, it easily follows that this means that the dimension of U is at most 1/2 of dimension of the big space. Here it's bigger or equal, and here it's precisely equal. But note, okay, that Lagrangian subspaces require that the signature has to be split. Require that the signature of the inner product is n for the same number. So the same number of pluses and the same number of minuses. Otherwise, you can show easily that you cannot have half-dimensional space which is isotropic. Okay, so people call this the split case or split signature. So if you have a positive definite inner product, then well, there is actually no vector which would be, there is no non-trivial subspace which will be isotropic. So already the non-trivial existence of isotropic means that you need to have some pluses and some minuses. Okay, so this is pretty much the same as for the symplectic case. And let's do it this way. So let's now say example. If, let's say, W is any vector space, then we can construct a nice example which is split signature. Then we define V to be the direct sum of W and its dual. We can call elements here X, and here Greek letters, it's an alpha. And the inner product is defined in a way that x plus y plus b, x plus alpha, y plus beta. If I have x and y here, alpha, beta in here, then I define this thing to be the pairing of alpha with y and beta with x. Because remember that now our vectors, now the x and y are vectors and alpha, beta are covectors, so they eat vectors and produce numbers. So this is now a real number. And note that, so in particular, x, y is 0, and so is alpha, beta. Which means that w and w star inside that V are Lagrangian. Okay, nothing too fancy. Okay. And let me call this example. Let me call this with this symbol. Okay, now something slightly more exciting. But only mildly. So this is unfortunately the necessary prerequisite. So if it's a little bit boring, then please bear with me for a moment, and let's do it exciting again, maybe. So let's say lemma. So yes. Okay. So let's do this example for a little bit more. So let's make this V as before. And now the claim is that if U inside V is Lagrangian, and the intersection of this guy with, let's say, W star is 0, then U equals the graph of a thing that I call the graph of B. Element of H2 star. I will explain what that means. And similarly, if the intersection with W is 0, then U is a graph of some beta which is in W, H2W. this means that once you specify, so this is a different way of saying that we have a linear subspace which looks as x plus b of x, or x in w. Picture to have in mind is something like w star, and there is something like this, which is the graph of which is u. Okay, so proof of this is very easy. So let's say the first one, so proof. So let's say the first case, this is 0. Well then, okay. I mean, already from the picture you can kind of see that if we assume that this with this zero intersection, it means that this thing cannot be like vertical. It is always leaning in some way, so we can always see it as a graph of something. It has the same dimension. This is half dimensional. This is half dimensional as well. It projects down, so it's a graph of something. So it's not too difficult. It's like easy to see that this is in fact a graph of some b. Except we don't know so far that this b has to be antisymmetric. So this is just some element in here. And okay, and then the only thing to check is, okay, we want it to be Lagrangian, so we want it to be isotropic. And so how do we check isotropy? So you take two things in there. You take that guy, so you take x plus bx dot, and you pair it y plus by dot, and you want that this thing should be 0. That's antisymmetry. That's isotropic. And okay, now how does the pairing works? You just pair vectors with covectors. So now these are the vectors, and these guys are the covectors. So you pair vectors with covectors, and you get presented that this is bxy plus byx. And hence the vanishing of this is precisely the antisymmetry. Okay, so this equality is the same as b in wedge 2. And the second case is just the same. You just swap w and w star. Okay, with that thing finally out of our way. There is a similar thing that we need to discuss. Okay, so let me phrase it as another lemma. So suppose that now we have a general general space V with some pairing. And now suppose u and u prime are Lagrangian in there. Okay, so forget about this special case. Let's take the general case. So suppose that they are Lagrangian and they have 0 intersection. And then we can build a map, which I call chi, from one of them, let's say u prime, to the dual of the other guy. And the map goes simply by I take an element u prime, and I map it into the inner product with u prime. Because inner product with something, this is a map in particular from u to real numbers. Okay, so I take the pairing with that, but restrict it to u. And the claim is that this map is an isomorphism. And our V, which because of this property we could have written it as u plus u star, u plus u prime, we now have a natural map to u plus u star, which goes by, which is essentially identity, which is the identity plus this chi map. So this is now an isometry, where here I take the inner product which we started with, and here I take the one which we discussed in the example below. Okay, so the moral of the story is that each time you have two Lagrangians which are complementary in this sense, then then essentially the space looks like this. So in other words, each choice of two complementary Lagrangians gives you an identification of the whole thing with this model. Is the statement clear? Good. Note that it's in order to have an identification of VU with this thing, I really need that. Although in the end you don't see U prime in here. In order to get such an identification, you need to choose both data. So it's not enough to just pick U, and then you say that I calculate U prime as somehow complementary because U is the complement of itself. Sorry, U is the orthogonal complement of itself. So you really need to specify both of these pieces of data to have an identification with the OVR space with this thing. One is not enough.
So if you chose two different U prime, you would get different isomorphisms
Yes.
within the same spaces.
Yes, yes, thank you. Okay, so how do we prove this? Okay. Yeah, okay, this is just simple. Okay. Oh. Maybe I don't need to. Should I prove this?
It's all good.
Yeah. So, well, these spaces have the same dimension because everything is finite dimensional. So it's enough to check that the map is injective. And to see that it's injective, you just, okay, so you suppose there is a guy in here. If you take a small U prime, which maps to 0, such that this maps to 0, which means that it's orthogonal to everything in U. But because it was in here, this is the same as to say that U prime is also orthogonal to U prime. So you have an element which is orthogonal to everything, to U and U prime, and hence it's orthogonal to the whole space, but that's not possible. So it has to be 0. That's one way. And the second way is easy as well. Okay, excellent. Okay, now we can go to fun stuff. Or fun stuff, not really funny, but any questions to this tedious algebraic work?
So in the proof you use the fact that U direct sum U prime is equal to V.
Yes, yes. And that follows because they are half dimensional and they have 0 intersection. Also, because it's just linear spaces, finite dimensional, then all vector spaces with the same, all vector spaces with linear product of the same signature are isometric. So hence there is really just like, they are all isomorphic to just one model, but not connected though. So there is still some interesting stuff happening. As well. Any questions or comments? I don't know, error existing while this thing tries. I think that's maybe more logistically convenient. Okay, now let's go back to geometry. It's still drying up. Okay. So we have linear algebra, so now let's talk about Courant brackets. first I will make a bold disclaimer in a second. So let me phrase it as follows. So to fix a manifold, smooth manifold, abbreviated as SMOOD. So we define the Courant bracket. Okay, there is a comment to follow, but a nomenclatoric claim. Define a Courant bracket on the following linear space. So we take the bundle, we take the formal bundle, kind of mimicking what we did before for vector spaces. So we take a formal sum of these two vector bundles. So sorry, we just take the sum of these two vector bundles and then we study sections of that. Okay, so what are sections of this? It's precisely like a pair of vector fields over M. It's the same vector fields on M plus one forms over M. Okay. Okay, so we define a bracket here as follows. If I get two such things, then this thing, maybe at this stage, should I? Okay, let me call this derivative with normal L, not curly, in anticipation for something that might or might not come later. So, comment. So if you look into the literature, then typically when the people say Courant bracket, they often mean the antisymmetrized version of this, and not this. Note that this thing is not antisymmetric. And instead, they would call this differently, Dorfman bracket or something like that. But I will argue, first of all, you'll never see the antisymmetrized version of that bracket ever. So we will always work with this one, and hence there is not really a reason to call it differently than Courant, because this is the thing that will give us a Courant algebroid later on. So I will just call this Courant bracket.
Perhaps just a historical reason.
Sorry?
Perhaps there's just a historical reason.
For the
calling it differently.
Yeah, no, definitely, yeah, because yes, there is. Yeah, I agree. So maybe from now on, let's just call it. We can automatically just call it a bracket. That's what I typically do.
So who was first, Courant or Dorfman?
Yes.
Dorfman.
Well, for this one, the bracket, probably Dorfman,
So why Dorfman?
because the object is called unambiguously a Courant algebroid.
Yeah, but it can have Dorfman bracket, no?
I would just call it a bracket. Okay, good. So now, why is this an interesting object? So note that it's not antisymmetric because, well, this thing is not antisymmetric in switching those two guys. But I want to pursue that this is in fact a good object. So let's do that. Let's make some claims about this object. So proposition for all u v w sections of this guy. Okay, so each of them is a pair of vector field in a one form. I will just call them u v w. Those formal sums. So for each of these things, we have the Jacobi identity. So as I mentioned, there is an antisymmetrized version of this bracket, but that antisymmetrized version does not satisfy Jacobi. So you can kind of choose, if you wish, between an antisymmetric one, which does satisfy Jacobi, or the non-antisymmetric ones, which does satisfy Jacobi, and obviously the second one is the way to go.
And is there some analog of Jacobi identity to the Courant bracket?
No, I mean, it's just like it fails, and there is like a failure.
So there is no
You can write it down like the failure bar, like
Yeah, yes, you can do that. Yeah, yeah. I mean, you can also you can rewrite the axiom, which I didn't say yet, but you can rewrite them in terms of that. But I will never ever use it object. So
Jacobi, but the consequences of Jacobi if it's excuse me.
Yeah.
Because Jacobi is
yeah, 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 yeah. Thank you. Okay, so how do we prove this? So instead of just plugging and calculating, there is a much better way. So, okay, so first observation. Okay, so there is two observations that I will start with. If you take a vector field and plug it in the first slot, then note that what happens is that you have lead derivative and lead derivative. So with just vector field here, this thing is the lead derivative. Okay, it's a very non-trivial observation. Okay. The second observation is that the bracket, as I wrote it up, so if you take any diffeomorphism phi, then just because of this thing here, all these kind of objects are natural differential geometric operators and whatnot, and you can easily see that this whole thing behaves nicely with respect to diffeomorphisms. I hope that's true. Yeah. So now putting these two things together and noting that lead derivative. So if you take essentially if you differentiate this thing. So if you would have a vector field x and you take a class of which generates some family of diffeomorphisms by the flow, and then you differentiate that, then you get precisely this thing for a special case when u is equal to x. Gives Jacobi identity for u equals to x. Okay, so if you differentiate it, then here you get like the lead derivative of this guy, which is essentially this lead bracket with u. Here you will get lead derivative, and here the identity, so that gives you this guy. Okay, maybe should have called them v and w. Sorry. So that this fits better. Okay, v and w. So that then really should give this thing. Okay, that's clear. So all that remains now is to check it for the case when you. Now we can take u to be just a one form. So now suffices to check for u one form. Okay, so now how do we proceed further similarly? So one thing to note is that there's a sort of natural filtration of this. So if you take two vector fields, then the result, note, okay, I didn't comment on it, but the way I wrote this stuff is that this is a vector field, right? This is a one form, same here, and this is why I put the parentheses, because this is again a vector field, and this is the one form part. Okay. So now if you take two vector fields, then you only get this contribution, so this thing is a vector field. Okay, I should write, no, it's okay. If I would take a vector field and one form, this is what? You can say that loud. And the people who are watching think that there is like no one in the audience. Okay, so it's a one form, you get this thing. And you get the same stuff if you do the other way around. Because the bracket is not symmetric, not anti-symmetric, you need to say the other way, and this is also one form, this bit. And what do I get when I get two one forms? Zero. Yes, actually it's better than a filtration. There is really a creating.
It's creating, yes.
Okay, that's pretty cool. So let's use that. So for instance, back to white chalk. Okay, so now the u is in omega 1. Okay, so now let's say, okay, if v is also in omega 1, then what happens? grading, then it's essentially that essentially tells us directly that. I mean, if I assign, I somehow should have noticed this. Okay, so if you assign this guy degree 0 and this one degree 1, then the bracket preserves this grading, right? That's what this one tells you. So if I have 3 things, then the degree of the total thing is just the sum of those things. But the sum can only be, it can only be non-zero if it's 0 or 1, right? If I would, like here, this is 1, 1, together that's 2, but there's nothing in degree 2, that's why it's 0. Okay, so it's enough actually, this thing shows directly that the only way you can have a non-zero thing at the end is that V and W are of degree 0. So only non-zero, potentially, if V and W are both vector fields. Otherwise, the degree of this is just too large and both sides are 0. Okay, so we just have one case to check, and that's pretty easy. So let's do that somewhere. Let's do it in a new board. Okay, so first one is that U is a one form and the rest is vector fields. So let's say, where am I here? Okay, so alpha, and let's call them Y and Z, kind of respect some sort of progression of letters. Now let me put both of them on one side. So let me put this thing on the left, and then I get alpha Y Z minus Y alpha Z. And now let's just plug this thing in. So this thing is simply the lead bracket. This thing is simply this bit, so minus I y of the alpha. And this thing similarly, minus I z alpha. And what do we get? We have a one form and a vector. Here we have the same one form and a vector. And here we have one vector. Another order. Okay, one form and vector gives us again this guy. So that's minus I of Z not the alpha. This guy is a same thing, so we have minus I, but oh sorry, how many minuses? Minus, minus, and there is another one. So minus I Z of D of that. And here we get vector and a one form, so that's the lead derivative plus lead derivative of y with respect to y of I z d alpha. Okay, and for now let's just compare calculation. So for instance here, remember the formula which we had the other day. So this thing, the whole thing, let's say, inclusion of lead derivative is the same as the commutator of lead derivative and the inclusion. Right? Okay. Here. And one of them cancels, so this one, right? The first term cancels with the last term here. This thing cancels with this one. And here we get IZ at the beginning in both cases. There is minus minus is plus. We get I of Z. And then here we get Ly of the alpha. Ly of the alpha. And in the other guy we get minus D I Y D alpha. But now again, using Cartman's magic formula, this is just D I Y plus Y I D. First term cancels the term there. And why is this thing 0? Because we get this square thing. So this is the end. So now everyone's persuaded that this is a reasonable object. Now what else do we have on the special case? Also on the special bundle. Note. inner product, given precisely by that formula that we had before. Okay, so x plus alpha. So it's in fact a pointwise inner product. Okay, so it's not really, you don't need to talk about sections, just at every point here, every point on M, you get the bundle is just the direct sum of two vector spaces, which is the tangent and cotangent bundle vector space, which are dual, so you get precisely at every point you have an inner product, and given by this formula. Now, this thing interplays nicely with the above thing, so let's raise it as another proposition. So if I have two sections U and V, then the antisymmetric part of the bracket, sorry, the symmetric part of the bracket is not zero, but it's given in terms of something that uses this inner product.
So is the signature of the inner product always the split one? or-
Yes. Yes. Yeah, that was the, yeah, because, for instance, because both T and T star here are Lagrangian, and as we mentioned before, Lagrangians can only get the split signature.
Or you can see the matrix is not anti-diagonal, which means it has zero trace, which shows that the signature is the sum of pluses and minuses.
Cool. Thank you. Okay, so how do we prove this? We can do it either directly, or let's just do it case by case. So, for instance, if we take, well, if both of these guys are one forms, then we know that the bracket zero. The right hand side is also zero because one forms are isotropic, so it's fine. Similarly, if U and V are vector fields, right hand side is again zero because vector field Tm is Lagrangian, and the left hand side reduces to lead derivative, and lead derivative of two vector fields is just the commutator, which is antisymmetric. They cancel out, which works. So the only interesting case is the one where we have a vector field and a one form. And the whole thing is symmetric in them, so we can just as well. Okay, so it is x's. Okay, it's vector field, and this is the one form. So let's calculate what this is. So that's that thing over there. Lead derivative of alpha with respect to x plus minus I x d alpha. And again, using the Cartan's magic formula here, this is d I x plus I x d. And the second one cancels with this guy, and what we are left with is d of ix alpha. But ix alpha is just the pairing of alpha with x, which is the same as inner products. So that's it. So note that although in the proof I kind of decompose it in vector product, vector fields, and one forms, the statement of this proposition and the statement of this proposition just talk about general sections of that bundle. Okay, maybe one last, maybe this stage a little less motivated proposition, but useful later. The following one. So let's make one more definition. So now we have this bundle, and we know that there is an interesting bracket. We know that there is a inner product. Now let's define what is called the anchor map. So let's say the projection. I will put a row from this bundle to the first vector. Okay, so simply just project. It's called the anchor map. It's a great definition. Just name something somehow. The last proposition says that this thing again, that there is a way where we can. Let me write it. So if I take two sections, U and V, and I take f to be a function, to say that now because there is derivatives happening here, then we should not expect that this bracket is bilinear over functions. It's only bilinear. This is a bilinear operation. Oh, I didn't even. Okay. As written here, this bracket is supposed to be understood as a map. It's a bilinear map on sections of this thing. But bilinear only over real numbers. Okay, so this whole thing is a module over smooth functions, but we don't care about that. In fact, when you multiply something by a smooth function, such as here, you take the section and multiply it by a function, then not only you will get this thing, but there will be a second derivative term which will look precisely, we'll use the anchor map, and it will look like this. So there is a term where u acts on f via the anchor map. Okay, is this statement clear? Okay, now the proof of that, let's do it just in generality. So let's say I take x plus alpha, I take y plus beta, and I multiply it by function f. Then what do I get? So I have now a new vector field, fy, and I have a new one form, which is f beta. So plugging that in, I get lx on fy plus lx on f beta minus y of f beta. Sorry, yeah, beta. No, sorry. Fy on the alpha. Yeah, okay. Now note that in this last slot, this contraction it's a pointwise thing. So here I can take the function out. So if this would be the only formula, then we are good. But we also have some other places where f is being derived, there is a derivative. So okay, of course, this one is lx x on f multiplying y plus f of lxy, and this guy will same. Write it lx f multiplying beta plus x on f plus f lx beta. And now if I collect the things, if I collect the guys where f went out, here, here, and here, then I get precisely f times the whole thing. That's given by this guy, and this guy. And what is left is these two terms, where I have x on f multiplying y plus beta. But x on f is precisely a row of x plus alpha thing on f, because row just kills the one from part. It just keeps the vector. So that gives the thing that we wanted. Okay, that was a little bit formal, but now comes finally the funnier part. Any questions for this part? Or comments? Or complaints?
Wasn't this one already supposed to be funny? No?
Yeah, it was. I had great joy in presenting this. Yeah, that doesn't make sense. Okay. Not so much time. Okay, brilliant. Okay, now let's make connection with all these funny geometries that we did before. I should stop this. Use the word funny. Okay, I see. Okay, so let me make a definition. So let's say, let me maybe call the whole thing. The new section, let's call it Dirac structures. Dirac. Okay. Structures. And generalized complex structures. still count this as part of this 2.1 section, which is introduction, because I haven't yet defined Courant algebras in full generality. But I think this is maybe the most interesting way to proceed, to kind of link this to complex and symplectic and other types of geometries. So now let's make a definition. So Dirac structure on M is a Lagrangian submanifold on Lagrangian subbundle of this guy that we had. So we still keep talking about T plus T star for today, which is involutive. And what does involutivity mean? It simply means that if I take any two sections of, let's call it somehow, let's call it L in here.
The same L as the Libra derivative.
Exactly. For historical reasons. So the bracket closes on this. So if you take two sections of that subbundle, then you again get a section of that subbundle. So there is kind of two maybe immediate. Okay, so that's the end of the definition. So yeah, okay. Well, okay. Anyone sees two particular Lagrangian subbundles of this guy? Let me recall the bracket. So, what are two natural Lagrangian submanifolds of this guy? Well, this guy and this guy. Good. Now, are they involutive? No.
The gradient now that you noticed before, that you were, no?
Sorry?
The gradient that you noticed before shows all these things, not that they say. The, for example, TM is degree 0,
Yes,
degree 0.
yes. I mean, I probably noticed this at some point, but I didn't notice it in preparation, but I should have used this. No, that's yeah, it's a cool fact. Yeah, so we have y for that grading. We have from the grading you can see we get the degree 0, so bracket closes on that. More explicitly in the formula, you see that two vector fields distribute another. If you have two one forms, then the bracket of one form is 0, again for degree reasons. So they are both actually Dirac structures. So examples: Tm or T star M are Dirac. Okay, now a little bit more generally. So again, I will use this linear algebraic fact that we had before. So if L is Dirac and it has zero intersection with the cotangent bundle, then we already know from the linear algebra analysis that L is actually a graph of some two form. I called it B before, but probably let's call it omega, which is now a two form. Okay, because at every point we just had the linear analysis from before, and we know that it has to be antisymmetric. It's a graph of something antisymmetric. And now because it's at every point, it's a differential two form. So now the theorem says that okay, that I find it maybe easier this way. So Dirac structures with which have this property, so they have zero intersection with this guy. They correspond via this graph thing precisely one-to-one with closed two forms.
Non-degenerate or?
No, just closed.
So it can be degenerate.
Yeah, it can be zero. So the moral of the story is that this bracket kind of like it gives you some sort of nice integrability condition. In this case, for this two form. So closure of a two form is some differential constraint, and you can see that you can encode this via this bracket in some mysterious way. And prove that. Okay, so proof. So this is our first link. This is the link to not really symplectic geometry because it's not, it doesn't have to be non-degenerate, but more like pre-symplectic, but also a little bit more general because pre-symplectic utilities require that the rank is constant of the form. So this is slightly more general, but roughly you should think of this as like this is how pre-symplectic stuff sits inside the story that we're developing. Okay, so now what is this bundle? So the bundle is the graph of this omega. So sections of that is simply vector fields plus omega that, where x runs over all vector fields. Note that this is the same thing that before we called, or this is exactly the same thing as contraction of omega with x. Okay. So what do we have to show? So we want to show that if you take two such things, and another such thing, so that's the only thing that remains. So yeah, so we know what actually here. I mean, I could have just as well said Lagrange, but here this was just sorry, because this was just the fact that it's antisymmetric. There was no integrability yet, but in particular for Dirac test too. But yeah, more generally, it's just Lagrangian. Now the utility condition tells us that okay, we want that if you take two such things, then you want that the bracket of this will again be fitting in L. Okay, it will be of the same form for some new element Z. So okay, so let's calculate what is this thing using that formula. So first term is the Lie derivative of x with y, and then there is some stuff. So there is like Lie derivative of this on this guy. You see that there will be some Cartan logic formulas appearing too. And then there is another term which is minus Iy of d of Ix omega. This is the vector part, and this is the one form part. So now in order that this thing sits inside here, because element of this precisely look like this guy. So in order for this thing to sit inside, this thing sitting inside is the same thing as saying that this thing is the inclusion of this guy in omega. Okay? So this inclusion, if you want to check, this is the same, right? So this thing is in here, even only if this thing is expressible as I of this into omega. So that whole thing. This thing has to be I of Lxy into omega. And this is for all x and y. Okay, is that clear? This is how you check if something is again of the form like this. This thing needs to be this thing included in omega. Okay? If you object, then say. Okay, so now we just need to verify this. So how do we verify this? So let's put it all on one side. Let's re-express this equation. Let's just kind of play with it and let's see if we can re-express it in some more useful way. So, okay. Let me just put it first. Let me just put everything to the left. So the equation just says this minus this guy. Okay, it's the same equation. Now let's just play with it. So again, using the Cartan formula, I guess maybe here. Inclusion of by commutator is the same thing as commutator inclusion minus the other way. Sorry. Inclusion of the Lie derivative is the commutator of Lie derivative inclusion. So it's this guy. Hopefully one of them should cancel. first one cancels with this thing, right? This thing. So what are we left with? It's just this term and that term, right? So this one will be plus, and this one will be minus. And as before, usual magic, this thing is just dix plus ixd, and you see that this, the first term kills that guy. So all that are left is I, y, ix of d omega. So this equality for all x and y is the same as this thing being 0 for all x and y, which means omega is 0. Omega is 0. Isn't that cool? Right. So what's next? Next, let's do the other case where the Lagrangian subbundle has zero intersection with T. Can anyone guess what we are aiming for? In there, in that case? Yes. Who said that? Good. Okay, so now as before, if L Lagrangian and L intersection with T and 0, then it follows that L is a graph of some element of H2 Tn, which in this case would be a B vector. Let me call it phi statistically. This is now a section of H2M. H2Tm, sorry. Okay, so this is just the Lagrangianity. But now what does the integral of the continuum correspond to? Theorem. Say Dirac structures with this property are in one-to-one correspondence with Poisson B vectors. Okay, so this is how Poisson geometry embeds into that magical bracket somehow. Okay, then how do we prove this? So first, maybe let's do some lemma. So, okay, this is a useful game to play, so let's play it. So let's suppose that we have a, this is a useful calculation to do in any case. So let's let this thing be more generally an isotropic subbundle. And let's say that we have some set of sections, E alpha, global sections of this guy, for some, I don't know, some set. I don't want it to be a frame or anything, just a set of these things, generating sections, all sections over smooth functions. Okay, I just mean that give me enough of these things such that any section of the bundle I can express as these guys, some of these guys multiplied by some functional coefficients. Okay, then the claim is that L is involutive if and only if it's involutive on these guys. So it's enough to just check this generating set. Okay. Obviously, if it's involutive, then this holds. saying that it's enough. Actually, if I check it on the generating guy, generating bunch of things. Okay, is the statement clear? So I don't need to check for all sections, it's enough to check it on some generating subset. I guess I can call it generated, right? Generating is a good name for it.
Well, generation.
Yeah, this is global. Okay. I'm not saying that if I have a given section that there is a unique decomposition, it's just, you know, it just. Okay, yeah. So that's good. Thank you. No, I don't want it to be a frame. I want it to be more than a frame in principle. Because I want it to be global. I mean, yeah. Because the bundle doesn't need to have a global frame. Okay, let's say generating. Okay, now proof. Not that I will need the isotropic for this. For this proof to hold it, please. Okay, so where is it? Okay, so let's say that I have two sections, U and V. And now let me just express them as in terms of the generating set. Again, the summation is assumed here. Beta. Okay, so this for some functions. Okay, so I mean, I don't need that they are uniquely expressive. I just say that take any functions such that this works. There is a sum, and now let's calculate. No. So what is the commutator of these guys? Not commutator, sorry, the bracket. So, and let's use the properties that we already know. So, one thing that we know, and it's no longer on the board, is that we know that if you have a two guys and multiplied by a function, then you know that you can take the function out, but you will get another term, which is the anchor. Okay, so let's do that here. Let's take this v beta out. And I get this guy and some e beta. Okay, you see it? Is it clear already? Okay. Then there is a second term, and the second term will look like a row of the first column, the first slot, u alpha, e alpha, acting on v beta, as acting because vector field acts on a function. And now let me employ notation where I will write the triple equality, where this means up to sections of that bundle. Okay, this will be modulo sections of that bundle. Because I want to show that this thing is zero modulo section of that bundle, namely that this thing actually is in the bundle. Okay. This notation means we want to check that this thing is in L. So anything that's already in L, we don't care about. So I will throw it away. So I will write this to be up to sections of L. And last thing is namely section of L, because E beta was a section of L, and this thing is just some function that multiplies it. Okay, so this is already simplified. So this is V beta. Okay, what do I do now? Now I have to. Well, now I would like to take this thing out. But in general, I cannot. So, well, because there is some derivatives hitting it. So, how should I do it? First, let me rotate this thing. So we know another axiom. We know that if you have u v, sorry, not axiom. We haven't axiomatized it, but it's a property. We know that the bracket is not anti-symmetric, but you know what the symmetric part of the bracket actually is. And note that because this guy is in L, and this guy is also in L, and L was assumed to be isotropic, this term is actually 0. So in this particular case, I can actually invert it and get a sign. Okay, and now I use the same formula here. So that will be V beta, U alpha, E beta, E alpha. And then there will be a second term. Okay, let me write it. E beta. Sorry, there's a minus. Just forgetting there's a minus here and there's a minus here. And the other guy will be simply rho on E beta acting on U alpha multiplying by E alpha. But again, E alpha was in L, so we can forget about that bit. So this thing is triple equality the same as this guy. Minus V beta U alpha E beta E alpha. So you see that if we know that these guys, combinators of these, the brackets of these E alpha and E beta are always gamma L, this follows, this shows that actually any section, I mean, that these U and V are as well. So actually, it's enough to check the whole thing on this generating set. Yep.
I'm not sure if I fully understand the difference between this E alpha guys being a frame of L and this statement that they generate.
So you see, so I could have equivalent. Okay. So we can have a bundle which is not topologically trivial, so which is not trivial. So it doesn't have a global frame.
Okay.
But I can always choose. Like I can always have a manifold, and I have some vector bundle over it, and I can always kind of choose some open set, which is small enough such that there will be a global frame in here. So I take that guy, I extend it in some arbitrary way to the whole manifold. I extend it by some partition of unity. So I will have like something that only lives here, but and a little bit around. So I can promote all these frames of this guy to the global thing, and I do it at every open.
Okay, and you take all of these.
And I take all of them. I could equivalently, maybe in an easier way, I could have just said that I would, because this thing is really a local condition. So I could just as well say that you do it locally and pick a frame. That would work in the same way. But yeah, is it good?
Yes.
Okay, very good. That's a good question. Thank you. Okay, I'll just finish the proof and then let's take a break. Okay, that's ideal. While I'm erasing it, you can try to imagine why I'm going to, or how I'm going to use this lemma in the proof. Just for the symplectic thing, we wanted to prove some statement, and it was supposed to hold for all vector fields x and y. This is kind of a dual picture. Now we will need to prove something for all one forms. All pairs of one forms. So sometimes it's kind of hard to work with one form, so I want to work with some generating set of one forms. One forms of some special kind. One forms which are easy to work with. Funny one forms.
Actually, you should avoid form at all because, according to the editor of physical review letters, editors of physical review letters don't know what the rest of forms are.
is an advanced course.
Not suitable for readers of physics.
You lost the half of wisdom.
Okay, so now we want to prove the theorem. Okay, so first of all, what is a bundle that we are studying? So it's a graph of a vector. So what is a graph of a vector? It means that I'm now looking at all alpha and then plus this thing which, this, so alpha is now a n1 form. Sorry, this is sections. Sections of L are given by all such things. And, okay, but now, okay, so does anyone see a good generating set of this, which is kind of convenient? Or okay, so this is generated by
Differentials of the coordinates.
oh yeah, that's even better. Okay, yeah. No, but coordinates are not okay. Yeah, I want to do it globally, or so. Let's just.
Differential functions.
Yeah, so this is generated by. I can just work with df's because famously any form can be written as a linear combination of some coordinate functions with some coefficients. Okay, so this plus df. Of course, now the index set I is like large. Okay. Okay. So yeah, again, because since this is a bundle, and any section of this I can write a bunch of these things multiplied some by some functions, and then summed over. Okay, so let's check it on this generating thing. Which, incidentally, now that we have a closer look at it, well, this vector field that we get from here. If this will be okay, we only really discuss symplectic geometry, but in that case, this is precisely the Hamiltonian vector field of F. But even in the Poisson geometry, this is how we define it. So let's call this object XF. Okay. And what is the significance of that object in relation to what we did before? We know that if this thing acts on a function, on another function, then this is the Poisson bracket. Okay, because recall that we define Poisson bracket for Poisson manifolds to be this guy. Okay, so that's the only thing that we'll need. Just let's call this object XF, and remember that if it acts on a function, it precisely produces a Poisson bracket. So yeah, with that in mind, this is just XF plus df. Okay, so now what does the involutivity mean? So again, as before, we want to have XF plus df, and we want to have second such things, xg plus dg, and we want that this thing is inside gamma of L. So it again is of this form. Sorry, it doesn't have to be this. It needs to be of this form. Okay, so now what is this guy? Using the formula which I accidentally again used, but hopefully now you remember this is simply L xf on xg. That's this guy, and then there is plus L xf acting on dg, and then there is minus I of xg d on this guy, but this guy is already d of something, so this just goes away. Okay, and also moreover, this thing, because later it commutes with d, this is the same as L of this guy, but this thing again, because now we have a derivative function, and it's the same as the vector field acting on a function, which is now the same as the Poisson bracket. Right? So this is d. So overall, summary is that we know that we We haven't used yet any assumption or anything. This is just writing things in terms of definitions. So we know that this thing is really LXF, XG, and the second guy is D of the Poisson bracket. Okay? So now, and the thing that we want to check is when this is inside gamma of L. Now, when is that thing inside gamma of L? Well, if it is of this form. What does it mean that this is of this form? It means that this is alpha, and it means that the first guy has to be pi of alpha. Okay, so this is the same thing as saying that the first guy here, LXF, XG, is pi of this guy. Okay. Involutivity is simply that condition. Now let's look at it a little bit more. So what do we have? On the right hand side, this is simply the X G. And this thing is really the commutator vector field. So we have vector field on the left, vector field on the right. How do we check when they are the same? So let them act on something. This thing holding for all f and g is the same as for all f and g and h. We have L, x, f. Let's write the vector. Commutator of xf, xg, acting on the function h, is equal to x, f, g, acting on the function h. But now what is this? Using this wonderful definition, this thing means that I'm first. This has two terms. First term is x of xg on h, but xg on h that's Poisson bracket with h, and then I hit it with xf, which means that I Poisson bracket with f. I have this one, then I have minus the other way. That's the left hand side. That's the left hand side, and the right hand side is simply the bracketing with f and g. And voila! So the thing that we get, hopefully, maybe with some, need to use the fact that it's antisymmetric a couple of times, but this thing is the same as the bracket satisfies Jacobi identity, which is the definition, the very definition of Poisson vector. That the induced Poisson bracket satisfies Jacobi. So that's the end. Any questions before the break?
Just put the program just to see the statement.
Prove the second case as the first one, but using this Lichnerovich differential and not well, you start with some Lichnerovich derivative with respect to this bilateral, and then show reduce it to the square to 0.
Right, that should probably work as well. So you mean that then you can show them in similar manner?
Yeah.
Okay, I believe that.
Oh.
Okay, let's compose it. Work on your own way. Should I repeat that? Okay, so there was further fun stuff in it. So far for Dirac structures, now let's do something similar. So let's say that a generalized complex structure on M, say, is a involutive and involutive Lagrangian submanifold, subbundle, subbundle. But now not of T plus T star, but of T plus T star, and then complexify it. Okay, so technically I have to see the complex linearly extend all the structures that we saw before: the brackets, the pairing, the anchor map. So, okay, so, but otherwise, I mean, I'm not going to write it because it really just means that. So you just take a complex. So this is like a involved. Okay, so this is a complex. Okay, let's put it here. Complex. The complex subspace at every point. So it's kind of like a complex version of the previous thing. And I require one more condition. I require that the same thing that we saw for complex structures. I require that the intersection with its complex conjugate is 0. Right? So this thing is a real object, and if I complex conjugate it, then there is a if I complex tensor with complex numbers, there is a well-defined complex conjugation of the whole thing. So that's what I mean here. And I want that it's kind of very much independent from it. So together they intersection is 0. In particular, because they are Lagrangian, so they are half-dimensional, it means that they actually span the whole bundle. If you remember from our discussion of complex structures, these were the two things that we want for integral almost complex structures. We want this, we want that. This is a very natural analog, except the involutivity now is not with respect to the commutator vector field, but with respect to this new bracket. Okay, so once again, it's like a complex version of the. You can call it a complex Dirac structure if you want. It's really that. But you want it to be satisfy this. Okay, and maybe let's one further sub-definition. So let's define a type of a generalized complex structure. Yes. So this is defined as the codimension of anchor acting on this L. So this thing will produce something in T complexified. So I mean really it's a subbundle. So this gives you a subbundle, and I want that codimension Courant or whatever. At every point I get a number.
So when you say it's subbundle, is it with that it's constant rank?
Okay, no. Or is it? No,
Yeah,
I
I
don't.
think it is right.
Is it?
Subbundle is bundle.
No. I mean, sorry, subbundle is a constant rank, but I mean, this thing doesn't have to be a subbundle. Sorry.
Yeah.
So so this is really okay. This type will really okay. So it's not a subbundle in general. So this type can change in particular. In principle, in general, it can change as you go over manifold. It's a pointwise thing. So type of this thing.
Right?
Yeah, at the point is the codimension of this guy in that point. Thank you. That's actually an important point. Yeah. Thank you. Very good. Okay. And so for example. This will be type 0 example. So what is type 0? It means codimension is 0. Codimension 0 meaning that this thing is actually surjective there. So L is mapped on the whole of this guy. So this kind of, if you look at the examples from before, then this should kind of remind you of, I guess, of these pre-symplectic examples. Like you would have, if you would have a graph of a symplectic or pre-symplectic form, then that thing looked like, well, that was something that, if you ignore the complexification everywhere, that was something that before, in the pre-symplectic case, in the first theorem we had before, like this L was sitting like this, and so if you project it onto the anchor map, which anchor map here is really just vertical projection down, then it would be surjective. So we want to have something similar. We want to have like, so let's say a graph of something. So let's say take this L to be graph of something. But okay. And then something rather be antisymmetric. Again, there is some complexification, but that won't change. I'm being a bit sketchy here, I'm sorry, but okay, well, I just want to kind of heuristically count the fact that there needs to be a two form in here. In principle, it could be a complex two form, but let me specialize to the case when it's like this for where omega was some two form. Real. So pick an ordinary ordinary smooth two form, and take I of that and take the graph of that, and that will be our L. So this is, in other words, just set of x plus I, and now I will need contraction. Like this. X vector field. So know that I couldn't remove the I. If I remove the I and I would have a graph of a smooth 1-2 form, then it won't satisfy this property, because then its complex conjugate will have a non-trivial intersection with itself. Okay, anyway, I mean, this is intentionally sketchier because I don't want to really make a theorem to prove, because I will need to talk about equivalencies of these things, and we are not there yet. So let me just phrase this example. If you give me a smooth two form, I can create a Lagrangian subbundle, complex Lagrangian subbundle. And now the first claim is that this guy being 0 is equivalent to omega being non-degenerate. I'm not sure if I want to prove that, but yeah, let's not prove that. So, but you can imagine that if there would be an x, which would a non-zero x, which would kill this omega, then plugging that x in here, this thing would vanish, and I would only have this x here. And if I complex conjugate it, then I could do the same thing. So there would be an intersection. So I would violate this. So it shows it in one direction. So okay, in either case, let's just take it as a fact that this extra condition, which is kind of natural, this is the thing that ensures that this is non-degenerate. And now the involutivity, because again, this is the same as we had before, except it's complexified, so nothing essential has changed, all the differential constraints stay the same, and in particular it's closed.
So in this framework, we don't replace I by other complex phrase, like it Wi-Fi, where phi is not 0 and pi?
Yes, I think so. Yes. Yes, in fact, the general claim is that what's the claim? Okay, like more. I think, yeah, right. So I think you can say again that if you want to have L which has 0 intersection with Tm complexified, maybe T star. I think this is the same as saying that this has to be graph of some object, capital omega, which is a complex two form, which has non-degenerate imaginary part. I think that's a true statement. So what you can say that using words which we haven't discussed before, you can show that like it's like you always get like a V shifts of this example if you want to have this condition or something like that. But anyway, I didn't want to talk about it. But yeah, thank you. That's a very good point. So that's the case where which is type 0. So the type 0, you can see that that was the type where you take this guy, you project it onto the Tm, and you'll end up with this guy. But since you could have taken any vector field, and you essentially span all the vector fields, so you get. Sorry, this was to be complexified. that's why it's type 0, because it's codimension 0. Okay, now okay, so let me just summarize it as a proposition. So if omega is symplectic, which is precisely what these two conditions say, then graph of I omega is a generalized complex structure. And okay, second example. This is the, I'm not going to prove it, but the maximal case, maximal type. Maximal type turns out to be this one. So one thing that I did not show it, okay, I did not want to talk about it, but anyway, like you can show in general from just linear algebraic considerations, right? Yeah, no, linear algebraic consideration. You can prove that if you have a manifold which admits a generalized. Okay, if there is a non-trivial generalized complex structure, then it means that M has to be even dimensional. For instance, here, symplectic has to be even dimensional, or even if it's not symplectic in general, it needs to be even dimensional. And then it turns out that the maximal type you can have this one. Again, not going to prove that, just wanted to talk this one example here. So let's start with let's start with almost complex structures. So let's say, so if L0, which is in Tm complexified, is a generalized, it's a, confusing the term, almost complex structure. So remember that from the way we discussed this before, it just means that it's involutive. It's involutive and it's precisely satisfied that L0 intersection L0 bar is 0, L0 with the whole thing is the whole thing. So L0 with L0 bar is the whole thing. And it's involutive. Sorry, not involutive, but it's almost. So far it's almost. Okay? I want to start with an example like here that I don't impose the integrability condition and I come to it. Okay, so let's say we have an almost complex structure. Now we can try to define this L, which is supposed to live in Tm, T star, M complexified. And I define it simply as L0 and then plus L0 bar below. Okay, this is my definition. Because recall that Tm complexified decomposes into L0 and L0 bar, this thing, and the cotangent bundle complexified decomposes similarly, L0 dual plus L0 bar dual, and I just take this Lagrangian subspace, which is these two guys. This is my L. Now, is this thing does this thing satisfy the conditions? Is it true that it's, if I intersect it with its complex conjugate, I get 0? That is true indeed, because if I take the complex conjugate, then I precisely get the other two guys. So that holds. Is it Lagrangian? Well, if I take any, well, it is, because I only need to check the cross pairing, and the cross pairing is 0 because this is precisely the dual of the other guy, not of L0. This thing pairs with this guy, this thing pairs with this guy. So it's Lagrangian. It's isotropic and multidimensional. So the only thing to check is involutivity. So now, involutivity. So how do you check if something is involutive? Well, you need to have two guys which live in here. So let's say, let's take two guys which live in L0 in the first summand here. Involutivity implies that this thing needs to be in here. Because again, recall that the bracket looks the way the bracket looks this. So applying the bracket to two vector fields is just the commutator of those two things. And that's precisely the condition that this guy is integrable. It's precisely the fact that the almost complex structure L0 is integrable. Okay, then there's another thing. We need to check that if I take something from here and something from here, that it is 0. This. Oh no, let me do the other one first. If I take two guys from here, then this is natural evolutive because they are covector. There are one forms and the bracket of one form is 0. This is zeros, which is automatically sitting inside L. That's good. So there is no condition there. And the only other condition that I get is if I have one guy from here and one guy from here. So gamma L0 and gamma L0 bar star. And this needs to be inside this thing, but I know from there that if I take a vector and I take one form, then the result is one form, so it needs to be in here. And this needs to be in gamma L0 star bar. Okay. This is the only thing remaining to check. Let's check that. Let's take a general section in here. Locally, recall that this thing means that if we have an integrable thing, which means that it's the same to say that L0 is really a complex structure. So there is really a complex structure underlying the manifold by the Newlander Dirac. So we have some complex coordinates, z and z bar, and this guy is precisely stuff that looks like something proportional to partial z. Maybe multiplied by some function. And this other guy, this is guy that lives in bar thing, and it's into dual, so this is the stuff that is dz bar, multiplied by some coefficient functions. Okay, I'm a bit sketchy here. Because this is, and I want to check that this thing is of the form, this thing looks like something which is of the second type. Something I'm ignoring the indecision. There should be some zi. What is this? And okay, so if I just calculate this thing, then what do I get? So I have a vector field, I have this thing, so the left hand side here is the lead derivative of that. So lead derivative with respect to z of this guy. Now the lead derivative acts in a way that if either it hits the function, in which case I have dz bar surviving, which is good, that's what I want, or I get lead derivative acting on dz bar, and that gives 0 because lead derivatives can skip over d, and then the partial z kills partial z of z bar is 0. So this thing is proportional to dz bar. Okay, so that's all. So there is no further condition coming from here. So it's only the integrability of the complex structure. So let me summarize the result. Although derived rather quickly here. So M is a complex manifold. Then this thing, which incidentally before we just called it this L0 for the case of complex manifold, that was precisely this T10. Then this thing is a generalized complex structure. Okay. There was a little bit of complexifications flying around here and there, but the result is that you should think of, remember there is these two particular cases of generalized complex structures. One of them is complex manifolds, and the other one is symplectic manifolds. framework, and in fact you can have some, some things in between, some things which sometimes behave like that, sometimes behave like the other one, or you can have maybe some interpolating stuff. That's pretty cool for various reasons, including what is called mirror symmetry considerations. Okay, that's essentially closes this part. Then there is one more thing I wanted to derive, and then I can give you the final definition of a Courant algebroid. Please, any questions? I apologize for this part, it was a bit fast, but I mean, it's not the main focus of what I wanted to do.
You probably said it, but there you used that the bracket is anti-symmetric on.
Oh yeah, because I didn't check it for the other case. Yeah, sorry. Yeah. I should have checked it the other way, but the symmetric part of the bracket is proportional to the pairing, and this thing is isotropic, so pairing is 0. So it's enough to check it one way. Thanks.
And you start from 0, like algebraically, and bar for complex quantification.
Yes. Modulo this insertion here, the rest of the stuff which we will do will be, the plan is to do everything in a smooth world, so we won't be talking, won't be seeing too much complex manifolds. Maybe. At least until the end, or late parts. Okay, any other questions? Okay, then if not, then let me recall what we have. Let's gather the stuff that we have. So we have a bundle, Pm plus P star M, and we found that there is some structure on it, potentially interesting. We have a pairing. We have a bracket. And we have this anchor map that also entered in some of the things that we've seen. And we noticed that this had, okay. That there were a couple of strategically thinking how to do this, so they will have to rewrite it again. So we saw that this was satisfying some bunch of axioms, so such that there was Jacobi identity. Then there was this thing that told us that if you have symmetric part of the bracket, this is proportional to this guy. And we saw this thing, which now there is one more claim that one further compatibility claim that this data satisfies with respect to itself. So does anyone have a suggestion about what that might be? So I want to write another condition that this satisfies, and it expresses some sort of nice compatibility of this structure. So can you think about anything like that? So, well, okay, this might look weird, but this thing says essentially that the bracket is a nice derivation of the operation that you multiply functions and sections. This thing says that the bracket is a derivation of itself. But there is also this inner product, which enters in this weird axiom. But is there some sort of compatibility? Well, you have some sort of bracket, so you can ask whether that bracket preserves the pairing. So that's the last claim. So, well, how do you usually phrase these things? So you want that this would be a real algebra, then this would be it. You would want that this is 0. So if you take a bracket U on the first slot or the second slot, well, this is a manifold, and this thing is really a tensorial field. It can vary. So you should really have that this is not 0, but this is pairing of V and W, and then act it on this result, and then you should act on this guy, but this thing is a function. But that's what we have the anchor for. So this is for all u, v, w, functions of tm, must be okay, so if you think about it, then this thing really says that kind of the derivation of the bracket of the pairing itself is, sorry, the action of u on the pairing itself is 0, because the action on the pairing is really the action on the result minus the action on the slot and on the other slot. Okay, so this is the natural foundation you might call invariance of the bracket. So let's prove that. This is going to be simple. So first of all, if this u guy was really a vector field, then we know that bracketing with u is the Lie derivative, but so is the anchor of u if you add some functions, right? So everywhere u appears, it just acts as a Lie derivative, and because this pairing was invariant under details, because the pairing itself was just a pairing of vectors and covectors, so that thing is invariant for any. Right? So again, if you differentiate that, then it precisely gives you this condition in the case when u is a vector field. Okay, so right. So for the vector field case, it's simply the diffeomorphism invariance of the pair. Okay, so that's done. So what remains is the other case when this is in omega 1. In that case, the left-hand side is 0, right? Because this row map is simply forgetting the one forms. So is there some clever grading argument that I could use here? Well, maybe you can think about that, but let me just prove it directly. Okay, so okay. U is a one form that we have. Okay, so now let's say that if V is a one form, this is essentially the grading argument. If V is a one form, remember this part is 0, remains to check this one. If V is a one form, then here we have a parent bracket of a one form and one form, which is 0. In here we have a bracket of a one form with something, which has to be a one form, or 0. But one form is orthogonal to one form. So yeah, that's essentially the grading. The argument by grading as before. That this thing is just trivially satisfied because those things are 0. And because of the symmetry in W, the same is true for W. So if W is in omega 1, that goes automatically. So it means that the only thing to check remains to check the case when U is a one form and these guys are vector field. U is a one form, V is a vector field, and W is a vector field. And in that case, that equality reduces to 0 equals that. So pairing of alpha, bracket of alpha and y and z plus y alpha z. Okay, we need to check whether it's 0, and that should follow easily because this guy was just the minus I y the alpha, which means that the whole thing here is minus I z I y the alpha. And the thing here is precisely the same, but with z and y exchanged. So this is minus I z the alpha, and the whole thing is, sorry, that was, yes, no, it's fine. There is minus I y I z the alpha. And the sum of these two things is 0 because here I have insertion of z y, and here I have insertion of y and z. So this is 0. Okay. So the pairing is invariant. argument would essentially be that if you want to have a pairing of two things and you want that it's non-zero, then one has to be vector field and the other one has to be one form. So together they need to have degree 1. Because vector fields are degree 0, one forms are degree 1. So it needs to be, whatever is inside needs to be degree 1. And since U was already degree 1, it means that the other two guys have to be vector fields. So that's a slightly quicker way. Feel like this is not doing anything. Okay, any questions for this? Because this is the end of this introductory part, and now let's do, we shall do the definitions of what this object actually is that we want to put out. And let me optimistically start here. So, part 2. Courant algebroids definition. Definition. A Courant algebroid is a vector bundle let's call it E over M together with some extra structure. So a bracket, most prominently, which goes from sections of that bundle, which is bilinear over real numbers, and it goes from, takes two sections and you create the third one. That's one. Second one is a fiber-wise inner product. Okay, again, this just means that every point, the corresponding fiber, which is vector space, carries a inner product, not necessarily positive definite, and it varies smoothly with the over the manifold. And finally, a vector bundle map rho from the bundle to Tm. So this is called the anchor. And note that when I say vector bundle map, that this is a sneaky way of saying that it's a map which preserves the base. So in other words, this is a collection of linear maps at every point. So I take a fiber at every point, and I map the tangent space at that point. Or M. Okay, so vector bundle map, it means that it's not like, I have two vector bundles and I jump from one fiber to another one, but it's a fibers over the same point. That's a pointwise thing, such that now come the axioms. So for all three sections of that guy, and for all functions of the base, we want to have the following axioms. So the first one is the Jacobi identity. Sorry, the Jacobi identity. Okay, I will use this one, but as discussed with Philip, I will comment on it later. So the one that we had before. So, I don't know, this thing you can call somehow if you want. Then there is invariance of the inner product. So says that the okay. So what did we have before? We had before that this thing was d of some function. But there we use the fact that if you take d of a function, you get one form, and one form is lived naturally in the Courant algebra. Sorry, in that object. Now here I cannot just say d because again I will have a one form, but one forms are not naturally living inside E. So, well, okay. So, okay, I will call it curly D, where this curly D is the following map. So it takes functions and it produces something in gamma of E. And how do I define this? So this is defined by the following. You take a function, you apply d to it, you get one form, which is secretly the same as section of the cotangent bundle. And now you remember that you have the anchor map. So the anchor map is this strange thing that goes from the bundle to Tm. So the row went from bundle to Tm. I have to take the dual of that. Then the dual of that map will go from the dual of this space, which is T star M, to the dual of this guy, which is E star. Okay, so I simply apply this thing pointwise. So I apply the dual of the anchor map, and I get something that's in gamma of E star. But now, finally, I can use the fact that we have a pairing. We have a non-degenerate inner product here, and that non-degenerate inner product allows me to identify E with its dual. It looks long, but if you think about it in this special case, then it just gives it D. So, okay, it's written long, but it's the only thing that you can really do. And that's the end of the definition. And note that probably I will, without any further mention, I will just automatically always identify E star within E using the inner product. That's kind of about it. Okay, so that's what a Courant algebroid is. It's a it looks pretty random if you see it for the first time, if you especially without the motivation that we've done, because so far we've seen that probably the important example of this is the structure we saw before. So, example, you take this guy with the structure from before. Namely, this one. So, right. So, if you regard it as a kind of generalization of this example, then it's kind of not that wild, but it's still kind of, it's like kind of, it's like 4 axioms. So, as was pointed out by Philip before, you can actually omit this axiom if you want, because it should follow from the one in here. From the third one, if you would, instead of W, you would put F times W, and then look at what it gives you, and use the same axiom again, and you should end up with this guy. So in principle, you can omit it, but yeah. So if you want to have like a minimal set of axioms, then you can do with 3 if you want, but it's I like to keep it around. But anyway, as you see, it's a rather long definition. So one of the goals of the course is that is to show you later on that there is like sort of more convenient ways to look at this. And so in particular, I don't have to remember all this bunch of random axioms. And in fact, we will progressively get to a framework in which it will be just like a half line of definition to say what that thing is, which is therefore arguably maybe a better viewpoint than this one. But this is kind of at least the historical, the way there was historically. It's just kind of people started to look at this bracket and notice that integrability of some interesting structures can be encoded in terms of this bracket, in terms of involutivity of some bundles under this bracket. then they kind of abstract it or axiomatize this thing, and they ended up with this more general definition. So okay, so okay, let's look at some more examples that are not this type. So one which is particularly, which is often overlooked, which is a pity, is the one where you take M to be a point. So I mean, point is a manifold, and so what do these things reduce to? So okay, if you take a point, then the vector bundle simply becomes a vector space. E is a vector space. Where is it? The anchor map is necessarily zero because the anchor map is mapping to the tangent space, and the tangent space is trivial. So here this map is zero. So the only two interesting thing that survive is the bracket and the pairing. Now, if you look at the axioms, then, well, the second axiom you can forget about. You can anyways forget about from what Philip said that it follows from the third one, but anyway, I mean, because the anchor map is zero and the bracket is linear, so the second one you can just forget. The last axiom will tell you that the bracket is in fact anti-symmetric because this D operator uses the anchor map, and this is zero, so the bracket is anti-symmetric, and anti-symmetry together with the first axiom tell you that this is in fact a Lie bracket. And the pairing is supposed to satisfy the third axiom. Again, anchor being zero, so it's just this guy, which is this is an invariant pairing, invariant inner product. So, Courant algebroid with M equals a point is the same as Lie algebras with invariant pairing. Invariant inner product, sorry. I use pairing and inner product synonyms. Invariant inner product. And such things are often called quadratic Lie algebras. Okay, so even in the case when you have a point, this thing still gives something, well, it gives you a non-trivial structure. And in fact, in some sense, you can regard this Courant algebroid as being sort of generalizations of Lie algebras with invariant products. And okay, and then maybe one last example that you get sort of trivially is that you can take M to be any smooth manifold, but you take the anchor map to be zero. Or let me say it like this. You just take anchor map to be zero, and then what this thing leads to, if you think about it, is that you have a manifold, and then E over M is a bundle of Lie algebras, quadratic Lie algebras. Bundle of quadratic Lie algebras. Because again, if the anchor is zero, then this curly D is zero, so the bracket will actually be anti-symmetric. But it will also be function linear, which is what second axiom tells you. So this thing being zero, we immediately can take functions out, so it's really a pointwise object. So it defines your bracket everywhere at every point. So it's just a bunch of quadratic Lie algebras which don't interact together, except probably they should, the family should be smoothly varying. So
I will call it quadratic, what is quadratic about having inner product?
Like it's a quadratic, it's like a bilinear operation. That's why, I guess why people call it that way. It has two slots.
It's given by a second order polynomial.
Right, yeah,
In the dual algebra.
And do you assume anything on the signature of this?
No, not at all, not at all.
Is there some kind of more useful choice, or like both, like positive definite or the split are kind of...
Well, in these examples, in this one the signature is split, and in this one it doesn't matter at all. So you can, in here you can take any, for instance, any semi-simple Lie algebra with the killing form would give you an example of such a thing.
And does the signature matter like anywhere in the theory? Or
Well, yes, in theorems which depend on the signature.
But are there like many theorems that depend on signature? Or is it
Uncountable many. No,
And I think when you want to define these Dirac structures and these things.
oh yeah, okay, so for Dirac structures you do want that, yes, that's true.
Isn't like 95% done with split signature? Because
Or
of
more,
this,
maybe
or
more.
99.
But okay, like if you care about whatever string theory applications that we might get to, then one thing that you can relate this to is the heterotic string, and there you would have not just t plus t star, but you would have t plus t star, and then locally you would actually throw in the bundle of Lie algebras as well. That one won't be split signature in general.
Lie algebroids are not broken, right?
Sorry?
Lie algebroids are not broken.
No, so good point. So we will get to Lie algebroids later on, but Lie algebroid is like a generalization of a Lie algebra. It's kind of more natural than this object, but in that case you can generalize Lie algebras to some kind of manifoldy, smooth context section, blah blah. And it turns out that actually that was if I remember correctly, that was kind of the historical thing that people knew how to do Lie algebroids. And they were trying to kind of make a analog of them where they would throw in this inner product. And they would add the compatibility of the Lie algebra of the bracket with the inner product. But it turns out that it doesn't work as obviously as one would do. And you have to give up something. You have to give up either anti-symmetry or the Jacobi identity. And that was one way that people arrived at Courant algebroids. That they realized that if you want to make a natural analog of quadratic Lie algebra, if you want to make an algebroid out of quadratic Lie algebras, then you need to give up something. Otherwise the conditions are so strong that you only get like, I don't know, something silly. So yeah, so they are kind of different with like the forking. So
Then there's this notion of Lie by algebroids, right? Which is
yes,
inside.
yes, that's that gives you a particular class of Courant algebroids. So yeah, that's actually how it arose. Like people were interested in like Lie by algebras, which is kind of you can describe them like this, for instance, and they were trying to generalize those. But actually, these two examples that I wrote, because they're kind of pathological, there is no anchor. These ones are actually Lie, but the most interesting ones are actually not. Okay. Wow. Still 5-10 minutes, right? Okay, good. Then let me make maybe one more proposition. So, okay, now we have the axioms, so we can try to play with them. Some people like to play with axioms. Let's do that. Proposition. So, one kind of further property that you might like, that you might think is a natural way for these things to interact, is that you can ask that we have this map, we have this anchor map that goes from E to Tm, and there's a bracket here and there's a bracket here. So why not asking them to be intertwining that thing? So, and the proposition is that this follows. For all you agree. Okay, so here, this is the bracket of E, section of E. And here, this is the bracket of vector fields. Okay. Okay, so the proof of that is kind of silly. So it actually follows from the first two axioms only. So you take your first axiom. So let's put 0 there. There is maybe a better way how to prove it, but I will do it this way. So this thing holds by for any Courant algebroids, this holds. For any now fix your Courant algebroid. You know that this is true for all triples of sections. So if it's true, then you can also, it's also true if you multiply your W by some function. Okay, this is a true statement because it holds for all sections. And I will just use the second maximum. So, for instance, here, write this thing as F, W, as row of V on F, and W, and here we can just directly do F plus row of U, V, and F, W. And this thing is really the same as this one, except we swap U and V. So, I don't know. Let's do this one with U and V swapped. Okay, so, well, there's unfortunately one more axiom use that we need to do here. So in the first guy, if you have a bracket of U with this nonsense, then you need to take the F further out. So we did F this plus row U on F and the second one as well. There's a function, there is a section, so I need to take it out. So I get row F. Oh, yeah, no, yeah, U of W plus row of U, row of V on F, and the whole thing times W. Okay, now I have everything. So the first term really is these four guys. Second term is these two guys, and this last guy is the same as these four guys, but with U and V switched. So if I now collect everything, so because I am, forget about this thing. Let's just look at the first and the last term. So since we are swapping U and V, then these two terms should cancel because this third guy will bring in these two guys with U and V swapped, but with a minus sign. So they will precisely cancel if you add this guy. And this thing, and the one from here will give you the Jacobi identity for U, V, W. So that one is also 0. Okay, so this one, and this one, and with the analogous thing here. So the only thing that remains is this thing with its counterpart and this guy, which is precisely what we want. So you get row U, row V on F minus row V, row U on F. The whole thing multiplied W and this term with minus. Which is, and the vanishing of this, the fact that this is 0 is precisely this statement. Okay, and there is a couple of more things that we can derive, and then we can proceed to exact Courant algebroids and their classification. But this fun stuff will be left for next time. So any questions? Complaints?
Can we generalize further? So we can think about differential forms as dual and change parity of vectors, right? So you can think about differential forms as you take the dual vector fields and change parity.
Yes.
What do you mean by change parity in this case?
Well,
You mean like
in the zeta order. So it's consecutivity of the vector space.
Ah, okay.
You mean like it's
forms are antisymmetric.
Yeah, and vectors are symmetric.
Yeah. So you take it as a derivations of functions. Your vector fields are dual with respect to algebraic functions and change parity. now you can complete it to the full picture. So you take a dual and parity of, so you take just dual to vector fields and vector fields with change parity. So you have these four pictures in green.
But so you were adding to T.
I will have C star change parity, and T change parity.
But how would we define the bracket on that thing?
Well, I'm asking.
Okay, well, I'm not sure.
Because this type of structures usually appears. Okay.
Yeah, I don't know. Sounds interesting.